We're going to start off multivariable calculus by going straight to the meat of the course, which is multivariable equations, multivariable functions, and the graphical ways of representing these things. Now, it turns out that in most math books, they don't really start with this. They delay the onset of this material, and instead they cover a couple of chapters that are mostly review of things that you've seen in previous courses. And while that material is needed for certain things that come up later in the course, they don't really come up until way later. So we're going to review those topics when those become pertinent. And instead, we're going to start off with the fundamental idea, the essence of multivariable calculus, which is multivariable functions. The reason why I want to start off with this immediately is because this is really the new stuff in the course. And this is really going to be the foundation for everything in the course. And it's important to develop a good understanding of it and to develop intuition. There's going to be a lot of visualization that you may not be used to based on your experience in previous classes. And so this is a challenge that we can handle if we start off with this topic early on. And over the course of the semester, we'll gain a better and better understanding of this material. Many, if not all, of the critical fundamental ideas in this course take place in either 2 dimensions or 3 dimensions, meaning they're about mathematical things that are happening in the xy plane or in xyz space. So in previous classes, you focused on 2 variable equations, equations that involve 2 unknowns. And the way that you graph these 2 variable equations is by drawing something in the xy plane. Typically, that's some sort of curve in the xy plane. Now, the next step is to study equations that involve 3 or more variables. And when you're looking at an equation involving 3 variables, the graph of that is the set of all points x, y, z in 3D space that satisfy that given equation. And usually, when you graph that, what you get is a 2-dimensional surface in 3D space as opposed to a 1-dimensional curve in 2D space. Now, rather than diving straight into really complicated surfaces and their plots, we're going to start off with simple surfaces that actually come up quite a lot in mathematics and in the sciences. And those are surfaces that have special types of symmetry. These are surfaces that are very simple in some sense, and that makes it easier to understand what they look like. So we're going to look at 2 types of surfaces first. The first class will be the so-called cylindrical surfaces, and the second class that we're going to look at shortly are the ones that have rotational symmetry about some sort of axis. Those are called surfaces of revolution. So what is a cylindrical surface? The idea is that it's not necessarily a circular cylinder. It's some surface that you get by taking a curve and dragging it in some third direction and generating a surface that way. So a feature that a lot of cylindrical surfaces have that you can just see from their equations is that even though they're equations involving 3 variables in principle, the equations are missing one of the 3 variables. So for example, z equals x is the equation of some surface in space, but it's missing the variable y. And similarly, the equation sine of z equals x represents some other surface in space, and again, that equation is missing the variable y. So it turns out that equations that are missing a variable are particularly easy to graph, and we're going to look at that next in this example here. In this example, we're asked to graph the set of points x, y, z in 3D space, satisfying each of the given equations. So for the first one, we have the equation z equals x squared. And even though you don't see a y there, from the context of the problem, we're talking about a surface in space. So that missing variable y is actually going to make the surface easier to graph, but nevertheless, we are talking about some surface in space. So how do you draw the coordinate system, first of all? The way that you draw the coordinate system is instead of drawing the x-axis sideways and the y-axis vertically, like you usually do when you're drawing things in the xy plane, just imagine that the xy plane now is some plane floating in space. And there's a third axis now, the z-axis, which is perpendicular to the xy plane. So just imagine that if you're in a room, the floor of the room is like the xy plane. And if you go to the corner of the room, at the edge, right above the corner, that is the z-axis. So the edge of the walls that point straight up is the z-axis, and the 2 edges of the floor are like the x and y axes. So the way that I'm going to draw the x, y, z coordinate system is I'm going to draw the x-axis in some direction, like that. And then I'm going to draw the y direction in some other direction. It's supposed to be perpendicular to the x-axis. And I'm going to think of the xy plane as being horizontal. It's floating in space. It's like the floor. So the y-axis is going to point in this direction, say. And then the z-axis is perpendicular to the floor. So it's going to be pointing straight up. All right, so that's my z-axis. So the way to think of this coordinate system is, just imagine that you're in a room and you go all the way to the corner at the bottom on the floor. The corner of the room is the origin in our picture. And the xy plane here is the floor. And the xz plane here is one wall of the room. And then the yz plane here is the other wall. So these three walls meet at the corner of the room, which is the origin in our coordinate system. This, by the way, is called the right-handed orientation of the coordinate system. The idea is that you use your right hand, your index finger points in the direction of the positive x-axis, your middle finger points in the direction of the positive y-axis, and then your thumb is forced to point in the direction of the positive z-axis. That's called the right-handed orientation of the coordinate system. If I made this axis my y, and this axis my x, and that upward pointing axis my z, that would not be considered the right-handed orientation because it doesn't match the three fingers on your right hand. So now, let's try to draw this surface in space. Rather than diving right into the 3D picture, what I'm going to do is, I'm going to go back to that equation and again note that there is a missing variable. The missing variable is y. So what that means is that we can draw what's happening in the xz plane easily because there's no y. And then we can generate the surface just based on that one picture. So on the side here, I'm going to draw the xz plane. And I'm drawing the xz plane because that equation involves only x and z. So what is the graph of z equals x squared in the xz plane? This is a quadratic equation. Z is a quadratic function of x. So the graph is a parabola. And that parabola opens up in the positive z direction because the square is on the x. So the graph of that equation in the xz plane is some parabola that opens up in the z direction. You can think of that curve that we just drew there as being one particular cross-section, one slice of this 3D surface that we're going to draw in this picture. And where is that slice? Well, the answer is that you can think of that slice as literally being in the xz plane in this picture. But because the equation does not involve a y, that's actually the cross-section parallel to the xz plane at any given value of y. So one of these cross-sections in the xz plane looks just like that parabola. I'm going to go ahead and draw that parabola here in the xz plane. I'm going to try to draw it with a little bit of perspective. Just imagine that this parabola is in the xz plane, which is this wall back here. Now, if I set y equal to 0 in that equation, I get z equals x squared. If I set y equal to 1 in that equation, I get the exact same equation because y doesn't show up in the equation. If I set y equal to 2 in that equation, I get the exact same equation. So what that means is that no matter what value of y you plug in, the cross-section at that value of y is always going to look like that parabola. So the way to get all the other cross-sections is by just copying this cross-section that we drew here. So I'm literally going to copy this parabola exactly as I drew it here, just one unit away from the xz plane. So if I copy this parabola here, I'm going to get that picture right there. And similarly, I can make a copy of this parabola in the back. So if I go in the negative y direction that way, those cross-sections should also look just like that parabola. So if I draw another parabola over here with the exact same shape as these, then now I have a bunch of cross-sections of this surface in space. And so the idea is that this is a cylinder. It's a cylindrical surface because all those cross-sections that are perpendicular to the y-axis, they all look the same. In some sense, I can generate the entire surface by taking one of those cross-sections and dragging it in the direction of the missing variable, which is in this case y. So how do I draw the surface? Well, the simple way to represent the surface is to connect these parabolas somehow. So just imagine that we look at these tips here, and we connect them with a straight line that runs in the y direction. It runs parallel to the y-axis. So I'm going to draw that line now. That line is supposed to be parallel to the y-axis. Similarly, I can connect these tips with another line that runs parallel to the y-axis. So if I connect those with a line parallel to the y, now I start to see the shape of the surface more easily. And similarly, I can connect the bottom of each parabola, the vertex of each parabola, with some line that goes in the direction of the y-axis. And now I get a better sense of what the surface looks like. It looks like a sheet of paper that's actually infinite, that's been rolled into the shape of a parabola. So this is often called a parabolic cylinder. So this is the fancy mathematical term for it. It's parabolic cylinder. The reason why it's called a cylinder is because it's not circular, but the cross sections perpendicular to the y-axis all look the same. That's what makes it cylindrical. And now it's called a parabolic cylinder because those cross sections are parabolas as opposed to circles like we have on a regular cylinder. So parabolic cylinder. Again, that is the sort of fancy mathematical way to refer to it. It's the mature mathematical way to describe this shape. But a much more common term that's used to describe this kind of shape is trough. So people more often call this a trough. And unfortunately, the spelling is kind of weird. It's T-R-O-U-G-H. It's pronounced trough. And that is like the typical way to refer to this shape here. Keep in mind that this surface goes in the y direction forever. It doesn't get chopped off. I drew an edge here because it's like we have a finite window that we're looking in. But the surface keeps going in this direction forever, in the y direction. It keeps going in the opposite direction as well. It doesn't get cut off there. This is just a finite chunk of the surface. And that parabola in that picture goes up forever. So this parabolic cylinder goes up forever in the z direction. If you understand the graph of this equation right here, then the equation in part B is not going to be that hard. It's very similar in shape. The difference is that in this equation, we're missing the x variable as opposed to the y variable like we did in this equation. But otherwise, the equation is quadratic. It looks like a parabola if you draw it in the yz plane. So we'll start off by drawing what's happening in the yz plane. I'm going to make my y-axis horizontal this time because I always want my z-axis pointing up. And now the picture is a parabola in the opening in the z direction because the square is on the y. So we're going to have a parabola that opens up like that. And now, how does this fit into the three-dimensional picture? Let me start off by drawing the coordinate system in space. And again, I'm always going to draw it with the right-handed orientation. So my x-axis is pointing this way. My y-axis is pointing this way. And my z is pointing straight up. So that cross-section that we drew in the yz plane, I'm going to copy it now and put it in the yz plane here in space. So I'll go ahead and draw that parabola with a little bit of perspective. And now what I'm going to do is I'm going to copy that parabola and drag it in the x direction, because that's the missing variable. So if I take this parabola here and I make a copy of it 1 unit away along the x direction from the yz plane, I'll get another parabola that looks like this. And if I make another copy of that parabola, but I put it in the back, in the negative x side, I'll get something that looks like this. So these cross sections that are perpendicular to the x-axis all look like that parabola that we drew up there. And the way to generate the surface is to connect these parabolas. So if I connect these tips up here with a line that's parallel to the x-axis, I get that edge there. And similarly, I can connect these points here with another line that is parallel to the x-axis. And the vertices of these parabolas at the bottom there all lie on a line that is also parallel to the x-axis. That's the bottom of this trough. So again, this is a parabolic cylinder. Cylinder because all the cross sections look the same when you take those cross sections to be perpendicular to the x-axis. And parabolic cylinder because those cross sections are all parabolas. And again, a more common term for this is trough. And the difference between this trough and that trough that we drew in part A is the direction in which the parabolas are being dragged. Here, the trough is running in the y direction. Here, the trough is running in the x direction. That crucial direction is the direction of the missing variable in the equations. So now let's think about the surface in part C. The equation there is y equals x squared. So again, the key feature, algebraically speaking, is that it's missing a variable. In this case, the missing variable is z. So I'm going to start off by drawing that curve in the xy plane. So now I'm going to make my x-axis horizontal and my y-axis point straight up, which is the typical orientation that we have for the x and y axes when we look at the xy plane. And in this picture, we have a parabola that opens in the positive y-axis because the square is on the x. So I'm going to draw my parabola opening up, just like that. Now, how does this picture fit into the three-dimensional coordinate system here? Let's think about these pictures here. The way that this parabola relates to this picture is, just imagine that in this picture here, you don't see the y-axis, but that's because it's perpendicular to that picture. The y-axis is actually pointing out of the board, perpendicular to that picture that I drew there. In this picture, the x-axis is not seen there, but that's because it's perpendicular to the yz plane. Similarly, in this picture, you don't see the z direction, but that's because it's perpendicular to the board. So just imagine that the z-axis, which is usually thought of as pointing up, is actually pointing straight out of the board in this case. So when we draw the picture in 3D space, that's going to be the cross-section of the surface in the xy plane, in the floor. And the surface is going to be generated by dragging that parabola in the z direction, which is upward. So let me go ahead and draw the coordinate system in space the way we usually do it, which is using the right-handed orientation. And now what I'm going to do is I'm going to sketch this parabola in space, and that's a cross-section, for example, in the xy plane. So I can draw that with a little bit of perspective. Now it's going to be a parabola on the floor in the xy plane here. So I'm going to draw something like this. That's some sort of parabola in the xy plane. And if I take that cross-section and I copy it, and I make it 1 unit higher, so I'm still making it parallel to the xy plane, but at z equals 1, for example, then I'm going to get a copy of that, which looks like this. So I'm just trying to copy this parabola as best as I can 1 unit higher. And I can also copy it 1 unit lower. So if I make a copy of this parabola down here, then I'll get another cross-section of my surface. And again, I'm taking my parabola and I'm dragging it in the direction of the missing variable, which is z. So now I'm going to connect these edges together. And that edge that I'm going to add to this picture has to run parallel to the z-axis, which is, again, the direction of the missing variable. So I'll draw a line connecting those tips there. And similarly, I can draw a line connecting these tips, just like that. And then the vertices of these parabolas are all going to lie along some line that is actually the z-axis in this case. So that is the picture for my trough now. And the trough is running in the z direction. So again, this is a parabolic cylinder. More often called a trough. And it looks just like these surfaces, except the trough is running in that third direction in our coordinate system. These three surfaces here are simple enough that we can actually form the shape using a sheet of paper. So in reality, you should be pretending that this sheet of paper is infinite. And the idea is that now you roll it into the shape of a parabola, and that gives you these trough shapes that you see here. The first one is this trough shape. If you roll your sheet of paper into a parabola, you make the edge, the bottom edge of the trough, go in the y-axis, the direction of the y-axis. So imagine just resting this trough on the y-axis. That gives you this surface. For this one, again, you take your sheet of paper, you roll it into a parabola like that, and you make the bottom edge of the trough lie directly above the x-axis. So rest the trough right on the x-axis. And for this surface over here, again, you take your sheet of paper, roll it into the shape of a parabola, and then make the bottom edge of the trough rest on the z-axis, and the trough opens up in the positive y direction because y is x squared. So that's what your surface will look like. So these three surfaces are essentially the same shape, except they're running in the three different coordinate directions. The equation in part D is x squared plus y squared equals 1. Again, we're supposed to be plotting a surface in space. And that equation is missing a variable. So I'm going to start off by drawing the cross-section based on that equation. This is going to be a cross-section in the xy plane, because we're missing z. So I'll start off by drawing the xy plane. The graph of that equation is a very famous curve. It's the unit circle. So I'm going to draw the unit circle in the xy plane. And the way you generate that surface is to take that cross-section and drag it in the direction of the missing variable, which is the z-axis. Now, you don't see the z-axis in this picture because the z-axis is perpendicular to that. So the z-axis is pointing straight out of the board towards you. And so to generate the surface, just take that circle, rip it off the board, and drag it towards you. And what you get is a cylinder with circular cross-sections. So this is going to be a circular cylinder. So let's go ahead and start drawing the coordinate system in space. I'm going to draw the x and y axes as usual. X going this way, y going this way. And then my z-axis is perpendicular to that, so I'm going to draw it pointing straight up. And the first thing I'll do is I'll copy down that cross-section in the xy plane. So that's supposed to be a circle in the xy plane with radius 1. So let me go ahead and do that now. So I drew my circle in the xy plane with radius 1. And now I take that circle and I drag it in the z direction. So I'm going to draw a vertical line on this edge of the circle. And then another vertical line on the other side. That'll help me draw the cross sections a little more easily. So another cross section is just like that circle in the middle, except drawn lower. And then another cross section is just that same circle, just 1 unit higher, say, up here. Now, typically when people draw surfaces this way, because those back sides of the circles are concealed, they're behind the surface, oftentimes people draw dashed curves there to emphasize that that's the opposite side of the surface, which is concealed by the front side of the surface. So a slightly better way to draw this so that it's more readable, more understandable, is to make those back sides of those circles dashed. That's optional, but it makes the picture look a little bit better. So this is called a circular cylinder. This is what people normally call a cylinder. It's a cylinder because all the cross sections are the same in the direction perpendicular to z. And it's called a circular cylinder because those cross sections are now honest to goodness circles. So the equation in part E is x squared minus y squared equals 1. And again, the key feature here is that we're missing a variable. The missing variable in this case is z. So I'm going to draw something in the xy plane. That's going to be a cross section. And then I'm going to drag that in the direction of the missing variable, which is the z-axis. So let's start off by drawing the xy plane. So now, what is the graph of x squared minus y squared equals 1 in the xy plane? This is actually a very famous curve that I'm sure you've seen in previous classes. Maybe not as often as the unit circle, but you've probably seen it at least once before. This is a hyperbola. And because the positive term is the x term, this hyperbola opens sideways. It crosses the x-axis and not the y. Now, if you're a little rusty with conic sections, it's okay. If you look at the very last page of these lecture notes that I typed up, I made a little appendix that reviews the graphs of 3 very basic conic sections. One of them is ellipses, and then the other 2 are hyperbolas. One of them is a sideways opening hyperbola, and the other one is a vertically opening hyperbola. So if you're worried about what the graph of this looks like, what I would recommend is that you refer back to the appendix. And later in this video, I'm going to go back to the appendix and I'm going to go through those graphs so you can review your conic sections. These hyperbolas will come up quite often in mathematics, so it's good to remember the graphs of these curves. So this, again, is a sideways opening hyperbola. It has one branch on the negative x side, and it has another branch on the positive x side, which is the mirror image of the branch on the left. And the way to remember that this is opening sideways as opposed to opening vertically is to just look at the intercepts of this equation. If you want to find the x-intercepts, what do? For the x-intercepts, you set y to be 0. If you set y to be 0 here, you get the equation x squared equals 1, and you can solve for x. X squared equals 1 means that x is plus or minus 1. So that means that the x-intercepts are -1 and +1. This hyperbola crosses the x-axis at x equals 1 and x equals -1. Now, if you try to do the y-intercepts, you're going to be in trouble, because to find the y-intercepts, you would set x to be 0. If you set x to be 0 here, you get the equation -y squared equals 1. But that equation doesn't have any real solutions, because if y is real, then -y squared cannot be positive, so that cannot equal 1. So this equation does not have y-intercepts. That corresponds to the fact that this hyperbola does not cross the y-axis. And that's a way to remember that this is a sideways opening hyperbola and not a vertically opening hyperbola. Crosses the x-axis, but not the y-axis. So now to draw the surface, what I'm going to do is I'm going to recall that the z-axis is perpendicular to this picture. So I'm going to take that hyperbola and rip it off the board and drag it in the z direction, and I'm going to generate two sheets that are rolled in the shape of hyperbolic branches. So I'm going to draw my 3D coordinate system now. My x-axis and my y-axis the usual way, and then I'm going to draw my z-axis pointing straight up. And now I'm going to try my best to draw these branches here in the xy plane in space now. So the first thing I'm going to do is I'm going to, just to make it easier on myself, I'm going to remind myself that this surface will be crossing the x-axis, but not the y. So those intercepts there, I'll mark them here. There's going to be an x-intercept at 1 and an x-intercept at -1. So I'm going to use those marks to help me draw the picture a little more easily. So I'm going to try my best to draw those branches here in the xy plane in space. So I'm going to have one branch that opens this way. I think that's good enough. I just want to make sure that it's big enough so that I have room to draw everything nicely. And there's going to be a branch on the opposite side here. So we're going to have a branch going this way here. All right, so now I'm going to make copies of these two branches higher up and down below. So I'm going to make a copy of this branch higher up. I'm going to go a few units up. And I'm going to make a copy of that there. And then I'm going to make another copy down below. I think that's good enough. And now I'm going to make copies of this branch on this side. But first I want to connect the dots on this side. So these edges here, these tips, are going to be connected by a straight line going this way. The turning points of these hyperbolas are also connected to each other by a vertical line. And these tips here are also connected to each other by a vertical line. So I've got one sheet, one hyperbolic sheet, which forms half of the surface. And then we've got another sheet on the opposite side, which is the mirror image of this through the YZ plane. So I'm going to make copies of this branch of the hyperbola here. I'm going to make a copy higher up. I'm going to try to align it with this one so the picture looks good. So I think that's good alignment there. All right, and now I'll make another copy of this down below. And again, I'm going to try to align it with this guy here so that the picture looks good. All right, so let me take a look to see if they're aligned. That's good enough. The pictures here don't have to be, Rembrandt quality paintings. They just have to have the key information, the essential shape. So now I'm going to connect the dots. So these tips here, I'm going to connect them with a straight line. And these turning points, I'm going to connect those with a straight line as well. And these tips are going to be connected as well. These are a little trickier to draw because they're in the back. They're concealed. So this part is solid, but then these ideally should be drawn with dash lines. And technically, I should be making this side of the hyperbola here dashed because it's in the background. It's being concealed. Okay, so that is the picture of our surface. It's a cylinder because all the cross sections perpendicular to the z-axis are the same. And what kind of cylinder is it? Well, those cross sections are hyperbolic. So this is called a hyperbolic cylinder. Again, it's cylindrical because those cross sections are all the same. And it's a hyperbolic cylinder because those cross sections are hyperbolic curves. All right, so the equation of the last part here, part F, is y squared over 4 plus z squared equals 1. And the key feature here is that we're missing the variable x. So we're going to draw the cross section in the yz plane based on this equation, and then we're going to drag it in the direction of the x-axis, and that's going to generate our cylindrical surface. So what is the graph of this equation in the yz plane? So I'm going to draw the y-axis and the z-axis. This equation is another famous type of equation. It's a lot like that circular equation, except it's got this factor of 4 below the y squared. So it's like a warped circle. And a warped circle is an ellipse. So this equation here is going to look like an ellipse in the yz plane. And again, if you're rusty with conic sections, go back to the appendix, the last page of this packet of lecture notes, and I go over the ellipse graphs there. So you can go back and try to figure out how to graph that if you're rusty with it. So let me go ahead and draw this ellipse now. In the y direction, the half lengths of the ellipse are 2, because this is y squared over 2 squared. So in the y direction, the ellipse crosses the y-axis at 2 and negative 2. And in the z direction, the ellipse crosses the z-axis at 1 and negative 1. That's because z squared is the same as z squared over 1 squared. So this is going to be an ellipse that has this shape here. It's longer in the y direction than it is in the z direction. So now the way to draw the surface is to copy this down in the yz plane and then drag it in the x direction. And in this picture, the x direction can't be seen because it's perpendicular to the board. So if I imagine the x-axis running this way, perpendicular to the board, I just take that elliptical curve, rip it out of the board, drag it in the x direction, and the shape that I generate is a lot like this one, except the cross sections are not going to be circular, they're going to be elliptical curves. So this is going to be an elliptical cylinder. So let me go ahead and draw the coordinate axes. I'm going to make my x-axis pretty long because this is supposed to be a cylinder running in the x direction. And then I'm going to make my y and z-axis a little bit shorter. So the first thing I'm going to do is draw this elliptical curve in the yz plane. So we cross the y-axis at 2 and negative 2, and the z-axis at 1 and negative 1. So that's my elliptical cross section. And then to generate the entire surface, I just take that ellipse and I drag it in the x direction. So I'm going to do something similar to what I did over here. Instead of drawing the other cross sections, I'm going to draw a couple of parallel lines, and that's going to make it easier for me to draw the other cross sections. They're going to be more easily aligned with the cross section that I already drew. So I'm going to draw a line parallel to the x-axis on this side. And then I'm going to draw another line parallel to the x-axis on this side. And then I'm going to add a few cross sections to this picture. We're going to have one cross section over here somewhere. It's kind of sloppy, but it's okay. And then I'm going to have another cross section somewhere over here. All right. So now, to make the picture a little bit prettier, I could make some dashed lines here. So for instance, this part of the elliptical cross section there is concealed by the cylinder. That's okay here, but this one is also concealed. So I can make these sides here dashed. All right, so that is the graph of our surface. And if the cylinder continues forever in the x direction, then I should also make these dashed. But I'm out of room here. So that's it. It looks a lot like this surface, but the cross sections are elliptical. So this is called an elliptical cylinder. So just like in the previous examples, we can make these shapes out of a sheet of paper by rolling them according to the shape of the cross section. So for this surface, we just take a sheet of paper and we roll it into the shape of a circle. And that's our surface. It's running in the z direction. For this one, it's the same thing, but now the sheet of paper is rolled into an elliptical shape. So this surface here is just this elliptical pipe running in the x direction like that. And again, it's supposed to be an infinite sheet of paper. So this cylinder goes in the positive x direction forever and in the negative x direction forever. And then for this, we need 2 sheets of paper. So take 2 sheets of paper, roll one of them into the shape of one branch of a hyperbola, and then the other one is going to be the mirror image. So that's a hyperbola, I think. And if you align those with the z-axis like that, and you make them cross the x-axis, then you get your surface. So, okay, that was a terrible attempt, but that's the idea. All right, so next we're going to do a quick review of polar coordinates in 2D, and then we're going to extend polar coordinates in 2D to obtain a new coordinate system in space, and that system is called the cylindrical coordinate system in 3D. And the reason why we want to do this at this point is because the polar coordinates are optimized to describe things that have rotational symmetry. And when we deal with surfaces of revolution, those are surfaces that have symmetry, rotational symmetry around some central axis. The polar coordinate system, or cylindrical coordinate system in space, is the ideal coordinate system to use when you're describing surfaces with that kind of symmetry. So recall that the polar coordinates in 2D, in the xy plane, are the variables r and theta. And the relationship between the polar variables r and theta and the Cartesian coordinates x and y are summarized by these equations right here. X is r cos theta, y is r sine theta. Now there's another equation that is actually very useful, and it actually follows from these 2 equations with a little bit of trig, and that equation is x squared plus y squared equals r squared. The way you get this equation from these 2 is by starting with x squared plus y squared, substitute r cosine theta for x and r sine theta for y. You'll end up with r squared cosine squared plus r squared sine squared. If you factor out the r squared, you're left with cosine squared plus sine squared. But cosine squared plus sine squared is 1. So what you're left with is r squared. So this third equation here follows from these 2. And the reason why I wrote this one down is because it's actually a very useful conversion formula that comes up quite a lot when you have rotational symmetry in mathematical problems. And then I threw in this 4th equation here just for completeness. We're not really going to be using it that much, but I figured I'd give you the equation that relates theta to the Cartesian coordinates x and y, because this is the equation that relates r to the Cartesian coordinates x and y. So it's nice to know that there's another equation that relates theta to the Cartesian coordinates x and y. So let's recall how to visualize r and theta in the Cartesian coordinate system. The grid that you see here is the famous polar grid that you probably learned about in a trig class. And the way that you generate the polar grid is by drawing a bunch of concentric circles. Those are all centered at the origin. And then you draw a bunch of rays that emanate from the origin. And the circles in this picture correspond to constant values of r, which stands for radius. And the rays in this picture, those lines that emanate from the origin, correspond to constant values of theta, which is the angle of rotation around the origin. So let's try to visualize the polar variables r and theta in this picture. Let me pick a point. Let's say I'm looking at this point right here that has Cartesian coordinates x and y. That means that we're x units away from the y-axis and we're y units away from the x-axis. So where are r and theta in this picture? To understand r, you got to imagine the segment that connects the point xy to the origin. So if you look at this segment right here, which goes from the point xy to the origin, that segment has a certain length. That length is r. So r is literally the distance from the point xy to the point 0, 0, the origin in the plane. Now what about the angle theta? The angle theta is the angle of rotation around the origin. So if you look at the angle between the positive x-axis and this segment that I just drew here, that counterclockwise angle around the origin measured in radians is the polar angle theta. And it's always measured counterclockwise around the origin, starting from the positive x-axis and ending at the segment that connects the point xy to the origin. So now let's try to think of what r, theta, and z look like in space. Those are the variables in the so-called cylindrical coordinate system. One 3D version of the polar grid in space is obtained by looking at the 2D polar grid and imagining that the z-axis points straight out of the board like this. So if you're thinking of the cylindrical coordinate system grid in space, when you look at it from above, what you see is exactly the same as what you see in the two-dimensional polar grid. And the way you get the third dimension is by taking the polar grid and just stacking it on top of itself repeatedly in the z direction. So if you do that, if you stack these polar grids on top of each other, what you generate is this cylindrical grid system in space. So now let's try to think about r and theta and z in this cylindrical coordinate system. So I'm going to pick a point in space. Let's say that I pick this point right here. Let's say that that point right there has coordinates x, y, and z. So the first of the three cylindrical variables that I'm going to talk about is z. That's the easy one. What does z look like in this picture? Z is literally the distance between the point xyz and the xy plane. So it's the vertical height of that point measured from the xy plane, or the vertical depth of that point from the xy plane if you're below the xy plane. So this vertical distance the length of that vertical segment from the point xyz to the xy plane, that is our variable z. So now the question is, what do r and theta look like in this picture? And again, you should think of r and theta as variables that replace the x and the y. So to understand what r and theta look like in this picture, just look at the picture from above. When you look at this picture directly from above, what you see is the xy plane, and those are the variables. The x and y are the variables that are getting replaced by the variables r and theta. So when I look at this picture from above, what I see is literally that picture right there. So the r and theta in space look just like the r and theta here when you look at the picture from above. So where is r? When you look at this from above, what you see is that little ray from the z-axis to the point. So that distance there translates to this distance here in this picture. So the distance from the point xyz to the z-axis now, that is our cylindrical variable r. And for the theta, again, you look at this picture directly from above, and what you see is that picture there. So the angle theta in space is the angle of rotation around the z-axis. That corresponds to the angle of rotation around the origin in the xy plane when you view this picture from above. So theta is literally the angle of rotation around the z-axis in this direction. So it's counterclockwise when viewed from above. So it's counterclockwise relative to the z-axis. And there's like a right-hand rule version of this, which is if you make your thumb point up in the direction of the positive z-axis, counterclockwise around the positive z-axis means the direction in which your fingers would roll on your right hand. So counterclockwise means in the sense of your bending fingers on your right hand. So that's counterclockwise. And that angle theta is measured from the positive x-axis. So from the half plane in the xz plane that corresponds to the positive values of x, that angle of rotation is the theta. So one thing to watch out for is that in the xy plane, r measures distance to the origin. But when you're in space, r doesn't literally measure distance to the origin. It measures distance to the z-axis. Distance to the origin in general is going to be greater. The distance from the point xyz to the origin is usually greater than r in space. Now, the exception is if your point xyz is literally in the xy plane, then the distance to the origin is actually the same as the distance to the z-axis. That's because you're starting with a point that's already in the xy plane. But if that point xyz is not on the xy plane, then r is distance to the z-axis, but not distance to the origin. So that's the big difference between the cylindrical coordinate system and the polar coordinate system in the plane, is that r is distance to the z-axis in general. So now we're going to use the cylindrical coordinate system to help us solve a lot of problems where rotational symmetry arises. So it turns out that cylindrical coordinate system makes a lot of problems easier when there is rotational symmetry involved, rotational symmetry around some central axis. So it turns out that these surfaces that have rotational symmetry, also known as surfaces of revolution, come up a lot in physical applications. In a lot of fields like physics and engineering, a lot of physical phenomena occur with rotational symmetry about some central axis. So this surface, for instance, has that special symmetry. And surfaces like this could be used to model a lot of different kinds of things. This surface, for example, could model the shock waves when an object hits some sort of surface. So for example, a meteorite hitting planet Earth will create shock waves on impact, and it will deform the landscape. And perhaps those shock waves can be modeled by some sort of surface like this. Another phenomenon that could be modeled by a surface like this would be the ripples on a fluid, on the surface of a fluid. When you drop a pebble in the water, for example, that generates ripples, which have shapes that are similar to this surface that you see here. And another thing that you could potentially try to model would be the vibrating membrane on a drum. When you strike the membrane on a drum, it vibrates and it generates ripples, and perhaps those ripples look somewhat like this. Now, the surfaces that you see in this example, Now there are a lot of other objects in applications that have rotational symmetry about central axes. So for example, in engineering, people study mechanical systems a lot, so things like motors, and a lot of parts in mechanical systems have to rotate around some axis. And so for that reason, these objects oftentimes have rotational symmetry about that axis of rotation. So again, the cylindrical coordinate system is going to be a benefit to us. It's going to help us deal with the symmetry and make problems easier to solve. Now, how would you describe a surface of revolution? One way to think of a surface of revolution is to imagine that you have a curve that gets rotated around some axis. So that curve is basically the radial cross-section of this surface. So those radial cross-sections are called meridional cross-sections. I usually just call them radial cross-sections. And that corresponds to the curve, the generating curve that was used to form the surface. So in this case, you might have a curve that looks something like this. If you take that wavy curve and you spin it around the central axis, you generate a surface. Now, the other kinds of cross-sections that are important here are the horizontal cross-sections. So if you notice, in this kind of surface, all horizontal cross-sections are circles. And that's exactly the meaning of being rotationally symmetric about some sort of axis. If you draw cross-sections that are perpendicular to the axis of rotation, those cross-sections should all be circles. They should all be concentric circles. So those are the cross-sections of the surface that are perpendicular to the axis of rotation. So you might wonder if there's a simple way to look at an equation and decide if the surface will have rotational symmetry about some central axis. And it turns out that if you imagine a surface that is aligned with the z-axis, meaning the central axis of the surface is aligned with the z-axis in your coordinate system, then z, which represents height, should just be a function of the distance to the z-axis. That's what it means for the surface to be rotationally symmetric. It means that you can tell how far up or how far down you are on the surface by simply knowing how far away you are from the z-axis. And that distance from the z-axis is the variable r. So if a surface has rotational symmetry around the central z-axis, then what should happen is the equation should involve only the variables z and r and not theta when you rewrite the equation in cylindrical coordinates. Again, the reason why is if you want to know how far up or down you are on the surface, all you need to know is how far away from that central axis you are. The x and y aren't really important. What's important is r. So again, the strategy for deciding if a surface has rotational symmetry around the z-axis is to take your equation and rewrite it in cylindrical coordinates and see if, when you simplify, the theta goes away. Because again, the equation should not involve theta because the shape of the surface should not depend on the angle of rotation around the central axis. All these radial cross-sections of this surface look like the same curve. A radial cross-section taken on this side should look the same as a radial cross-section taken on some other side. These two cross-sections that I just drew here have different thetas because the angle of rotation is different for these two pieces, but the shape should be the same no matter what theta you pick. So let's try to use this reasoning to analyze surfaces that have rotational symmetry around the z-axis. All right, so in this example, we're asked to graph the surface z equals x squared plus y squared. We have not seen an equation like that yet. The surfaces that we've looked at so far have been cylindrical, so that means that there was a missing variable. Here we've got all three variables. So now, turns out that this surface is rotationally symmetric. The way you see that is by rewriting this equation in cylindrical coordinates. Remember, the cylindrical coordinates are r, theta, and z. So the way that you convert this to cylindrical coordinates is to replace x with r cos theta and replace y with r sine theta. Now, turns out there is that formula, that's a special formula for conversion from Cartesian to polar. It says that x squared plus y squared simplifies to r squared. So we don't really need to substitute x equals r cos theta and y equals r sine theta in that equation because we already see x squared plus y squared, and that turns into r squared in polar. So if you write this in cylindrical coordinates, this equation becomes z equals r squared. Notice that there is no theta in this equation. The fact that there is no theta in that equation means that this surface has rotational symmetry around the z-axis. So let me make a note of that. There is no theta here. So what that means is that we have rotational symmetry around the z-axis. And that's good for us because it's going to make the graphing problem very easy. So how do I graph the surface? The key here is that while the original Cartesian equation had all three variables, when you convert to cylindrical, now there's a missing variable. Theta is missing. So we can draw this thing in the RZ plane. And then what is the role of theta? Theta is the angle of rotation around the z-axis. So if we know what this looks like in the RZ plane, then we can rotate that and generate our entire surface. Rotating corresponds to varying the theta. And again, the reason why this is rotationally symmetric is because that equation does not depend on theta, which is the angle of rotation. That means that all radial cross-sections, no matter what theta you pick, all those radial cross-sections look the same because that equation does not involve theta. So the way to graph this is to start with a picture in the RZ plane. Now, when you draw the RZ plane, you don't have negative values of r. In this class, r will always be positive or 0 because r is literally the distance to the z-axis. So we never have negative r values here. So when you draw your RZ plane, you don't draw the entire RZ plane. You just draw the half of the RZ plane that has positive r's. So I'm going to draw the z-axis pointing straight up. And I'm going to draw the half r-axis that has positive values of r. So now the question is, what does z equals r squared look like in the RZ plane? So now in the RZ plane, this looks like a parabola. it's opening in the positive z direction because the square is on the r. So when I draw the curve z equals r squared in the RZ plane, I get this shape right here. That's z equals r squared. And again, the missing theta in this equation means that you can generate your whole surface by dragging, so to speak, in the theta direction. But what is the theta direction? The theta direction is not a linear forward direction, it's a direction of rotation. It's a rotation angle. So the way you generate your surface is by taking that cross section and rotating it around the z-axis. So if I rotate that curve around the z-axis, I generate a surface. So let's think about what that surface looks like. If I take this parabola here and I spin it around the z-axis, what I generate is a surface that has the shape of a bowl. It's going to be a parabolic bowl opening up. So when I draw my 3D coordinate system, I'm going to have the x-axis going this way as usual, the y-axis going this way as usual, and the z-axis going up this way as usual. And again, when you take that parabola and you spin it around, you generate a bowl shape that opens upward, and that cross section, that vertical cross section, is a parabola. The horizontal cross sections are circles. So let me draw those in blue. Those horizontal cross sections are circles because this surface has rotational symmetry. And this bowl goes up forever because that parabola goes up forever in the RZ plane. So the mathematical term for this bowl shape is a paraboloid. So it's like parabola, but it has OID at the end there. So this is a paraboloid. And the horizontal cross sections are perfect circles. So for that reason, this is called a circular paraboloid. So circular paraboloid, again, because the horizontal cross sections are perfect circles. So we just finished sketching a surface that we hadn't seen before, so I think the best thing to do now is to check our work. And to check our work really easily, really quickly, I'm going to use a little grapher app that I have on my Mac. The grapher app is already built into all the Macs. So if you have a Mac, you should already have the app in there, even if you've never used it before. The way to find it on your Mac is pretty easy, actually. You can click on the Spotlight search and just type in grapher, and then the application will open up automatically. In fact, it's such a powerful application that I use it to make a lot of the pictures that we see in the lecture notes and in the homework as well, and on tests. So you'll see that it's a really cool app and you can do a lot with it. Now, if you don't have a Mac, there are a lot of other graphing apps that are easy to use, and I can tell you about them if you ask me during office hours. I'll give you some suggestions. Now, I'm going to go ahead and open up the grapher app and plot that equation, z equals x squared plus y squared. So first thing I'm going to do, just to show you how to find it, you go to the Spotlight search, open up the Spotlight search and type in grapher. And there you go. Just press enter. It opens up the grapher app. And when it opens up this window here, you get a choice between a 2D graph and a 3D graph. So if you select 2D graph, you'll draw curves, but if you select 3D graph, you'll be able to draw surfaces. So I'm going to select 3D graph. And notice that it's going to give you options for the default here, frame or window. So I'm going to pick the white one there. That's a pretty good one. So choose. And we see this XYZ coordinate system here. I'm going to do that to make it stop spinning. OK, so in this picture, the arrow going this way is the x-axis, the arrow going that way is the y-axis, and the arrow going that way is the z-axis. So I'm going to go ahead and type in the equation that we just graphed over here. We've got z equals, I just have to type in x squared plus y squared. So x squared plus y squared. And the annoying thing about the grapher app is that when you do an exponent, to get out of the exponent, you have to use the right arrow. Otherwise, you'll keep typing in that exponent. So now that I've got my equation typed in there, I press enter. and I see something that looks like a parabola, so it looks pretty similar to what we sketched. To get a better sense of what this looks like, I'm going to rotate it around. So I'm going to look at it from the top, I'm going to look at it from the bottom. So if I rotate it around, look at it from the top, now we are inside the paraboloid and we're looking down onto the vertex. So that bottom right there, that's the vertex. And I can also look at it from below. If I turn it around this way, we see the paraboloid from below. So there you go. That's confirmation that the surface sketch that we made was accurate. We did it without a computer. We did it by using rotational symmetry and cylindrical coordinates. And going forward, those cylindrical coordinates are going to be super, super helpful for us. All right, so let's get some more practice with cylindrical coordinates and surfaces of revolution by looking at this example right here. So consider the surface of revolution generated by rotating a two-dimensional hyperbola, like the one shown in this picture, around the z-axis. So you got to imagine that our surface of revolution has its central axis aligned with the z-axis, and we take this meridional cross-section, this radial cross-section, which is a hyperbola, and we spin it around the z-axis to generate our surface. Our job is to find the Cartesian equation of the surface that you get by rotating this curve around. So this idea is going to be useful for us because it's going to give us a way to come up with equations for shapes that have rotational symmetry. And these equations we can come up with from scratch without any help. So let's try to do this. So the first step is take your cross-section here, your meridional or radial cross-section, and spin it around the z-axis and generate your surface. So when I take this curve here and I spin it around the z-axis, what kind of shape do I get? So I take this curve here and I spin it around the z-axis like that, and the type of surface I get is basically a funnel shape. So if I take this curve here and spin it around the z-axis, I generate a surface that has this kind of funnel shape. So when I rotate, what I end up with is my surface in space. I'm going to draw my x and y axes the usual way. And I'm going to draw my vertical z-axis like that. And the way that you draw the surface is just make a few radial cross-sections and then make the horizontal cross-sections based on these circles. So one cross-section, for instance, would be this cross-section here. And then we've got another piece on the other side going like this. And then we've got another radial cross-section going this way, like that. And then another piece on this side, like that. And then I can just add a few horizontal cross-sections to this picture. Those are all circles. And then the other cross-sections are a little bit harder to draw, but it's the same idea. So that's the three-dimensional surface that we end up with when we rotate this hyperbola around the central axis. So now our goal in this problem is to come up with a Cartesian equation of this surface. And we're going to start from scratch. We're not going to be given an equation. We have to come up with it ourselves. So how do we do that? So the key here is start with the radial cross-section on this side. This curve right here, you should be able to come up with an equation for that curve in the RZ plane. So can you think of the equation of a hyperbola that has a branch that looks just like that? Now remember, the negative r values are not relevant. So don't worry about the left side here. Think of just the right side here. This branch of this hyperbola is the mirror image of the branch that is in the first quadrant. So do you remember how to come up with the equation of this curve right there? So this curve up here is a very familiar type of curve. It's called the reciprocal function. That curve up there has equation z equals 1 over r, for example. Now there are a lot of hyperbolas that look like that. I'm just picking one of them. The most famous one is z equals 1 over r. So again, in this problem, we are able to come up with our own equation here. So the problem just says come up with your own equation that might work. So a good candidate for that hyperbola up there is 1 over r. But we're interested in this branch down here. So if we know the equation of this hyperbola up here, what's the equation of this hyperbola down here? This is just the mirror image of this one. It's the reflection of this through the r-axis. So to get the equation of this part, we just take the negative of that. So the equation of this curve down here should just be z equals negative 1 over r. So z equals 1 over r is a hyperbola that occupies quadrant 1 and 3. And again, we don't care about the left side of the picture because r is positive here. If z equals 1 over r occupies quadrants 1 and 3, then negative 1 over r, z equals negative 1 over r, will occupy the other two quadrants, 2 and 4. And again, we only care about positive r here. So r is greater than or equal to 0. In fact, r can't be 0 because it's in the denominator. So here, r is strictly greater than 0. So now, how do you come up with the Cartesian equation of this surface here? Well, it's easy now, because we have the equation of that radial cross-section in the RZ plane. And then all we do is just convert this equation into Cartesian coordinates. So you have to remember how to write r in Cartesian coordinates. The key there is x squared plus y squared is r squared. So r is the square root of x squared plus y squared. That's the conversion formula that we're going to use to convert this equation into the Cartesian equation of this surface. All right, so I scrolled here to give myself more room to write the answer. So we found the equation of a radial cross-section. Remember the radial cross-section in the RZ plane is this curve right here. And we said that a good equation for that would be z equals negative 1 over r, where r is positive. And when we rotate, we generate our funnel shape, which is going to look something like that. So that's our surface. So in the process of going from RZ coordinates to Cartesian, we have to use the conversion equation, which is x squared plus y squared equals r squared, which means that r is the positive square root of x squared plus y squared. It's not plus or minus, it's positive because remember, r is distance to the z-axis, so it's positive. So now if we use that conversion formula, then this equation becomes z equals negative 1 over r, which is the square root of x squared plus y squared. So that right there should be the Cartesian equation of our funnel-shaped surface. Z equals negative 1 over the square root of x squared plus y squared. Now, since we came up with this funnel equation from scratch, we should check it on the graph wrap. So let me go ahead and open up the graph wrap and just run through it and make sure that we are getting the picture that we're supposed to be getting. So I'm going to open up the little shortcut that I have on my dock here and select 3D graph and select the white frame there. And I'm going to move this a little bit lower so you can see what I'm typing. All right, stop spinning there. Good. Okay, so now remember the equation that we got was z equals negative 1 over the square root of x squared plus y squared. So I'm going to go ahead and type that in there. So I'm going to do a fraction. So the division key, that generates a fraction. I'm going to put negative 1 on top. And then on the bottom, I'm going to put square root. And the name for that is SQRT. If you type SQRT, you'll get square root. So then it's x squared. So move out of the exponent position with the right arrow and then plus y squared. So I've got z equals negative 1 over square root of x squared plus y squared. So I'm going to go ahead and press enter and hope that I get a funnel shape. All right, so that's promising right there. That looks like a funnel. Let me see if I can move this a little bit higher just in case. So it kind of looks like a funnel, but it looks like it's getting chopped at the bottom. So perhaps I can play around with the zoom here. So if I zoom in, There we go. We start to see that funnel shape. Now I'm turning it upside down. Let me move the window up a little bit higher. So that's pretty obviously a funnel shape. Notice that this funnel has asymptotes. Okay, and the interesting thing in Math 200 is that asymptotes can come in a lot of variety. So one asymptote that this funnel has is a vertical asymptote, which is an axis. It's the actual z-axis. But then it's got another asymptote, which is actually a plane. So this funnel approaches the xy plane, but it never actually touches it. And so the entire xy plane is like an asymptote. So asymptotes in multivariable functions can have very different types. So they can be lines, they can be planes, they can be surfaces in general. So let me see if I zoom out in this picture what happens. So now we don't really see a little tail on the funnel there. That's because the resolution that I have in the settings are not good enough. But I could increase the resolution here and try to get a zoomed out version of the funnel, and then I'll have a really, really thin piece coming down from the bottom there. But if I zoom back in, let me zoom in one more time. There you go. Now we can see the funnel from the top. We see the depression there in the hole, and if we turn it around, we'll see the inside of the tunnel from below. Let me see if I zoom it in one more time what happens. Okay, so now we see the hole is bigger because we zoomed in. And now what happens when we look at it from below? Oh no. Oh no. Oh, okay, there we go. All right, yeah, that's definitely a funnel. All right, so success. We came up with an equation that has just the right shape that we wanted. All right, so now let's see if we can use these ideas that we've developed so far to come up with the equation of a donut-shaped surface. So let's try to find the Cartesian equation of a donut-shaped surface. In mathematics, the donut shape is called a torus. So that's like a fancy name for a donut. And we want the axis of symmetry of the donut, the central axis, to be the z-axis. So let's start off by making the donut hole have a radius 1. And let's make the donut thickness be 1 unit in radius. So what does that mean? So the donut has a hole in the middle. The radius of that hole in the middle should be 1. And then if you slice the donut vertically, you get 2 little circles. And each of those 2 little circles has a thickness of 1 unit in radius. That's what we're told to do. So how do you generate a donut? You got to think of that generating curve that you spin around to generate the donut. And that generating curve is simply a circle. So the idea is to generate a donut. You draw a picture in the RZ plane. Maybe I should make my R axis longer. I need plenty of room for the donut and the donut hole. So I'm going to make my R axis longer than usual. This is my Z axis. So how do you draw something here so that when you spin it around the z-axis, you end up with a donut? The curve that you should start with is a circle. If I take a circle and I spin it around this z-axis here, taking this circle here and spinning it around will generate your donut. So the problem says that the donut hole should have radius 1. That means that this distance here should be 1. And then it says that the donut thickness should be 1 unit in radius. That means that this should also be 1 unit in radius. So this value on the r-axis is 1. This value on the r-axis is 2. And this value on the r-axis is 3. So what would be the equation of this circle in the RZ plane? That's the first step. We need to come up with the equation of one of these radial cross sections. So for that circle, the equation is simply the unit circle in the RZ plane, except it's shifted 2 units in the direction of r. So if you just had the unit circle in the RZ plane, it would just be r squared plus z squared equals 1. But because this circle is shifted 2 units to the right, it's going to be r minus 2. That accounts for the shift of 2 units in the r direction. And then plus z squared equals 1. So that is the equation of the radial cross section. So now when you rotate you end up with your donut shape. And I'm going to try to draw a donut shape. These are hard to draw, but I'm going to try. Here's my Homer Simpson version of a donut. There you go. That's as far as I'm going to go with fanciness. So now my z-axis is in the middle. And the z-axis goes through that way. And the origin is right in the middle there. So the x-axis is actually pointing this way. It comes out through some location here. And the y-axis goes this way, goes through the inside, and it comes out through some location there. So this is the x-axis, that's the y-axis, that's the z-axis. And again, these cross-sections are circles. These radial cross-sections are circular curves. So this is roughly the picture of your donut surface. So now, what is the Cartesian equation of this donut surface? You take this equation here, and then you just convert it to Cartesian. So remember, r is the square root of x squared plus y squared. That's the conversion formula from polar to Cartesian. So the equation of the donut, the torus equation, will be this equation right here with r replaced with the square root of x squared plus y squared. So it's going to be this parentheses, r becomes square root of x squared plus y squared. And then we have the minus 2. And then close parentheses squared plus c squared equals 1. So in theory, this, when you graph it, should look like a donut. That's the Cartesian equation of the torus. All right, so what do you think I'm going to do now? I'm going to check my donut is OK. So I'm going to open up my grapher. And I'm going to select 3D graph, choose, and I'm going to scroll a little bit lower here so you can see the equation that I'm typing in. So notice that the equation starts off with z equals, but that's not the way that we wrote the equation. We started with square root of x squared plus y squared minus 2 quantity squared and so on. So I have to type that out, so delete it. And I'm going to open parentheses. Inside we're going to have the square root, so sqrt parentheses x squared, and then plus y squared. And then we also have a negative 2 after that. And then that whole thing gets squared. So that's looking kind of complicated, but we're past the rough part. And then it's plus z squared. And then that equals 1. So that's the equation of the torus that we came up with based on the cylindrical coordinate system approach. So that's our equation. So now when I press enter, I better see a donut shape. Otherwise, it's going to be embarrassing. So press enter. And we do get a donut. Actually, it kind of looks like those Lifesaver candies more than a donut, but that's because of the color and the glossy, settings on the app. You can change it to make it look more like a donut, but I'm happy with this. So that's obviously a donut. That works pretty well. I'm going to rotate a little bit so you can see it from different angles. And maybe I'll play around with a zoom as well. So if I move this a little bit up and I zoom out, what does it look like? Okay, that's a tiny donut. So now if I zoom in, now you have openings here. And there's a simple reason why we have these cuts here. So these cuts are coming from the fact that there's a finite window. Like on a graphing calculator, there's a finite window. And your window in space is a box. So if you chop some region with a box, obviously you're going to cut out certain portions of the surface. So these openings are the result of that box, that invisible box that is the window of our graph. So that's why you see the openings there. And you can see the core of the donut in there. And what happens if I zoom in even more? Okay, so now you just see the core. So that's not very interesting looking. So I'll zoom out again. And there you go. That's our donut. So success. One more time, right? Cylindrical coordinates were used to come up with that equation of the torus, and it works out pretty well.